Hello friends, I am Amir Nizami and today we are going to study free vibrations of viscous damped single degree of freedom system. So let's start. So first of all, we will write the equilibrium equations. So dynamic equilibrium equation we know mu double dot plus cu dot plus k of u is equals to 0. Because we are studying the free vibration of viscous damped system. So m here is the mass, so mu dot is the inertial force. This cu dot would be damping force or damped force, and k of u is spring force, or here we state it as restoring force. So inertial force, damping force, and the restoring force, and the sum of all is equals to 0, means external force acting on it is 0. Now m is the mass of the single degree of freedom system. So first of all, we will just make a idealized single degree of freedom system. So we can have a mass dashboard system. So here we can see it is an idealized single degree of freedom system, where this shows the damping coefficient and this is the spring which is showing the stiffness of the spring or restoring force restored, and it is the mass due to which the inertia would generate. So it can also, for an earthquake engineer, generally any building we, any structure we idealize, such as if this is a portal frame, or so we will just take the slab or beam combination as mass here, and we will assume the column as massless. So we will just generalize it as a single degree of freedom system. So we will just idealize it as mass here, lumped mass, and this would be the height. So these are the idealized single degree of freedom system. It can also be idealized as this, or this structure can be idealized as this structure. So where mu double dot plus u dot plus ku, where u double dot states u double dot is nothing but d2u by dt square. U dot here is du by dt, and u is the function of t, where u is the displacement with to time. Okay. Now, so we have seen that mu double dot plus u dot plus ku equals to 0, where mu double dot is the inertial force, cu dot is the damping force, and k of u is a spring force or restoring force. And then we have seen that a single degree of freedom system we have idealized, and for this single degree of freedom system we have written this equation for free vibration cases. So let's see. We will write it again, the equation mu double dot plus u dot plus k of u is equals to 0. So we will just divide it with m. So u double dot plus c by m u dot plus k by m of u is equals to 0. Okay, so now we will write, we know c is called the damping coefficient. C is called damping coefficient. Okay, and we will write this equation now, u double dot plus c by m. So now c by m, we will give c by m equals to 2 xi omega n. Okay, c by m we are writing it equal to 2 xi omega n, and omega n square is k by m. So we can write omega n as under root of k by m. Okay, now we will just know that what is omega n. So omega n is called the natural frequency of the structure or of the single degree of freedom system, because the stiffness of the single degree of freedom system and its mass, so it is called the natural frequency. It is, and c by m is equals to 2 xi omega n, and we can write xi as c upon ccr. Okay, so ccr and xi, so this xi is called damping coefficient, this xi is called damping ratio. And this c is called damping coefficient, and this cc are called critical damping coefficient. So here ccr is critical damping coefficient. Okay, so now we will write c by m as 2 xi omega n into u dot plus k by m. Instead of that, we can write it omega n square into u is equals to 0. We will give it equation 1. Now to solve this, because we can see here it is a double dt u by dt square means second order differential equations, so we can solve this second order differential equation. So let us assume u of t as e to the power st. Okay, so we know that first order derivative would be u dot would be equals to s into e to the power st, and u double dot would be second order differentiation would be equals to s square e to the power st. Okay, so now let's say these are the equation 2, this all three are equation 2. So now we will substitute equation 2 in equation 1. So what we will get, u double dot, so s square e to the power st, so plus 2 xi omega n s into e to the power st plus omega n square e to the power st is equals to 0. So here we can get s square plus 2 xi omega n into s plus omega n square, and e to the power st would be equals to now 0. Hence we know that e to the power st can never be equals to 0, because it is our trial function, or you assumed it. If we have assumed 0, then there is no solution, we know. So this can't be equals to 0, therefore it implies that s square plus 2 xi omega n of s plus omega n square must be equal to 0. Okay, so now we will get the roots from here. So in this page we will see what would be the roots. So s would be equals to minus 2 xi omega n plus minus root under 4 xi square omega n square minus 4 omega n square upon 2. So we can say that s would be equals to minus xi omega n plus, we can tell s1 as s1 minus xi omega n plus under root xi square minus 1 into omega n or into omega n, and s2 would be equals to minus xi omega n minus under root xi square minus 1 into omega n. Now we will have some cases here. So case 1, first case we will say that if the inside value the xi is greater than 0 and less than 1, this is the criteria, then we know that inside would be the imaginary roots would be there. So therefore we can say s1 would be equals to minus xi omega n plus iota times under root of 1 minus xi square, because iota is imaginary part which is equals to root times minus 1. Okay, so if you will put that, minus 1 would be common and that should be equals to 1 minus xi square, so therefore it would be 1 minus xi square and iota will come outside, which is the imaginary value. So first root would be this much and second root s2 would be equals to minus xi omega n minus iota under root 1 minus xi square, and omega n is also missing here, so omega n. So we will get this value. Okay, and this value we know omega d we replace, which is called a damped natural frequency, is nothing but equals to omega n under root 1 minus xi square. So omega n we say only natural frequency, and omega d we say damped natural frequency or damped frequency, damped natural frequency or damped frequency. Okay, so now we can also write it as minus xi omega n plus iota omega d, and it would be minus xi omega n minus iota omega d. So these are the two roots, so therefore we will get the general solution for it. So we will replace it with u. So we can say u homogeneous solution because it is free vibration, so there is no external forces acting, so we can say that the homogeneous solution would be equals to C1 e to the power minus, so sorry, we know the solution is C1 e to the power S1t plus C2 e to the power s2 t. So we will put the values of s1 and s2 here. So let's put the value. So u of h1, u of h is c1 into e to the power s1 is minus xi omega n plus iota omega d plus c2 e to the power s2 is minus xi omega n minus iota omega d, and with the independent function, that's t also. So here let us see, yes, t is there, so s1t and t. Now we can write it c1 into e to the power minus xi omega n into e to the power iota omega dt plus c2 e to the power minus xi omega n into e to the power minus iota omega dt, and t is here also. Now what is the common here? We can see iota omega dt is here positive and here it is minus iota omega dt. Okay, so what is the common here? We can see so we see that minus xi omega nt is common here, we can take it out. Now c1 into e to the power iota omega dt plus c2 e to the power minus iota omega dt. Now we know that Euler's formula is there, e to the power iota theta. We generally write this equation, so it is also called Euler's formula, that cos theta plus iota sin theta. This is the value, e to the power I theta is cos theta plus iota sin theta. So it is the imaginary part and it is the real part. So now we will just break this formula, as theta here represent that we are having e to the power iota and theta would be here replaced with omega dt. Okay, omega d into t would be replaced. So we can write it cos of omega dt plus iota sin omega dt. So let's replace it. So e to the power minus xi of omega nt, so c1 into cos of omega dt plus iota sin omega dt now plus c2 into, so e to the power minus iota omega dt is here, it would be replaced with e to the power minus iota theta is called cos theta minus iota sin theta. This is the formula for this value minus of I theta. So c2 into e to the power, so cos of omega dt minus iota sin of omega dt. Okay, so we can solve it, minus xi omega nt into this c1 cos of omega dt and here c2 cos of omega dt. So we will just have c1 plus c2 cos of omega dt, and we can write plus here iota would be here, so iota times c1 here would be positive, so c1, and here minus sin omega dt minus c2 into sin of omega dt. Okay, so from here we can see that, as we know that the trigonometric functions are always real valued. Okay, so we can replace it and we can write it as e to the power minus of xi omega nt. This constant we will replace it with another constant and we will write it a, and this constant we will replace with the another constant value which would be replaced with b. So we can write it as a cos of omega dt plus this value would be b sine of omega dt. So this imaginary part, due to the knowledge that we have the trigonometric function as real valued, so we will get this solution. So this would be the first case, which is underdamped case. Okay, now we can just have a quick review that we have considered xi is 0 to 1 and we got two roots. So this was the real part and this was the imaginary part. Okay, here same two roots we get. Now we know the homogeneous solution as c1 e to the power s1t plus c2 e to the power s2t. So s1 and s2 we got two roots, so we have just put those two roots here and we have just solved and we get the homogeneous solution for underdamped case. Now we will go for the second case, but before that we will have these a and b as a constant, so we have to also know that how to solve. So if the homogeneous solution is having any constant, so for solving those constant we must have the initial conditions. This means initial displacement or velocity, initial velocity would be given there, and if it is second order differential equation, so two initial conditions must be given to solve this problem. So we will have this. So first of all we will write the homogeneous solution here. U of h was e to the power minus of xi omega n t, and we can write a or b or a1 b a2, so a1 cos of omega dt plus a2 sine of omega dt. Okay, so now its differentiation with respect to time, you know homogeneous solution for that would be, let's differentiate it. So first we will differentiate. So if we differentiate it, so it is u and it is v. So u, then differentiate these value, so it would be remain same, it would be u, and we will differentiate v now. So this value, so a1 cos of omega dt, so a1 is constant, omega d would be here and minus sign would be there. Now this would be sine of omega dt plus, now we will differentiate it, so a2 constant, omega d would come outside, sine is cos of omega dt. Now you, we have done. Now we will just differentiate, so we will keep this as constant and we will differentiate it. So let's differentiate it first. So we will have minus xi omega n and e to the power minus xi omega nt into a1 cos omega dt plus a2 sine omega dt. Okay, so now we will have the coefficients to solve the coefficients a1 and a2. So from these two initial condition would be given. So at u of t equals to 0, we will have some value, whether it is 0, 1, 2, any initial values would be there. U naught we have replaced it, and u dot of t equals to 0 means initial velocity would must be given, so we will just replace it at u naught dot, so any values it may be. So we will just put the value for this. First, u of t equals to 0, u at t equals to 0 means u naught is equals to, we will put t equals to 0 in the equation 1, we will say it equation 1, we will say it equation 2, So we are just substituting in one equation. So t is 0, so it would be value 1. A1 cos 0 is 1, so a1 and sine 0 is 0, so this would replace a1 would be equals to u0. Now we would have the second equation, so we'll put t equals to 0 in the second equation. That would be u0 dot. We know that initial condition at t equals to 0 is u0 dot, so we'll just put the value. So now e to the power minus xi omega n t equals to 0, so that would be 1, so it would be 1 value, exponential value, minus a1 omega d sine omega dt, t 0, so sine would be 0, so whole 0, a2, so we will have a2 cos 0 is 1, so a2 omega d would be there, one term. Now here if we will put t equals to 0, so this value would be replaced with 1 and this would be there, so minus sine xi omega n, and then a1 cos 0 means a1 would be there and a2 would be 0. So we are having now u0 dot as a2 omega d and xi omega n a1. So we can replace a1 with u0, because from the equation 1 we got u0, a1 is u0, so from there we can get a2, value of a2 as u0 dot plus xi omega n into u0 upon omega d. So now we can write the solution, homogeneous solution, as u of h of t would be equals to e to the power minus xi omega n t into u0 cos omega dt plus u0 xi omega n u0 upon omega d into sine omega dt. So this is our general solution for this equation when xi is between 0 and 1, means under damped cases, because xi is between 0 to 1, xi is 0 to 1.